So I'm going to talk about calibrated fairness in bandits. I'm the bald guy here, and in the spirit of continuing these jokes about early morning presentations, I'm bold enough to come to the early workshop and present our work. So most of us are from Harvard, except for Christos, who is currently at Chalmers University of Technology. So I was really hoping to spend like 5 minutes or so in motivating why machine learning tools are important for fairness, but I guess I don't need to do it for this crowd. So I'm just going to state here that basically what we want to achieve in this work is some kind of analysis of why it is important to analyze uncertainties in fairness in sequential decision-making frameworks. Certainly, it is the case that many of fairness-aware decision-making procedures do repeatedly interact with individuals or groups of individuals, and they can sort of, by gathering data of them, make these procedures fairer over time. So basically, we want to analyze some kind of fairness metrics and see how they evolve over time as we gather more and more data about individuals. So arguably the simplest but yet informative framework for analyzing sequential decision-making under uncertainties is this multi-arm bandit framework. Just to recap, in multi-arm bandits, we have a choice, k choices, and we need to select one of them. This decision-making is done over t step of independent time rounds, and at each time step we select one of k arms, and this brings us a certain reward. Now this reward is stochastic, meaning that it's sampled from a certain underlying probability distribution function that is not known to the decision maker. And so the goal is basically to design selection policy pi that can possibly be random, and a standard goal in multi-arm bandits is to basically maximize the expected reward mu, which is basically the same as saying that we want to efficiently learn which arm brings us the highest expected reward. Okay, so how can we reason about multi-arm bandits and fairness? Well, there are arguably different ways, but I'm going to here present what, in my opinion, is the simplest way of reasoning about fairness. So suppose that we have two groups, and at each time step, these groups sample representative individuals. And now a multi-arm bandit decision algorithm needs to select between the two individuals, so red individual and blue individual. And of course, multi-arm bandit doesn't have a good knowledge of the qualities of these two individuals. However, over time, as we gather more and more data, we learn properties of groups. Okay, so at some point, MAB algorithm can actually use this group statistics in order to determine which groups lead to higher utility, so which groups lead to higher rewards. So basically, we can say that groups are arms and individuals are basically reward realizations in multi-arm bandit framework. Now, of course, it's not that simple because we also need to impose some fairness constraints. And there are different possible fairness constraints that can be imposed. And of course, we can start with the prior work. So Joseph et al. Already noted that fairness should be studied in a multi-arm bandit framework. And they had this nice notion of meritocratic fairness, which basically says that a worse arm should never be more favored over a better one. So more formally, they define the notion of weak meritocracy, which states that with high probability for all time steps t, if a certain arm has a mean reward greater than another arm, then this arm should also have higher selection probability than the other arm. And even though it's simple. This notion of fairness actually brings us with some interesting insights. First of all, the authors show that standard algorithms such as UCB do not actually trivially satisfy this definition. So some modification to these algorithms are needed if you want to incorporate them into a fairness learning framework. And secondly, and more importantly, there is a fundamental utility gap between fair algorithms and unfair but optimal algorithms. Okay, so now that I praised this work, what else can we do? Well, obviously, there's little to be done here unless their math is wrong, which I highly doubt. So maybe we can sort of improve on the definition of fairness. We can always argue that you can impose different notions of fairness, constraints. Okay, so our reasoning about weak meritocracy is that it has basically two drawbacks. First of all, it's not smooth in a sense that it allows decision-making rules that select always the best arm, even though this arm might be only slightly better than the other arms. And secondly, it's not strictly meritocratic in a sense that if a decision maker adopts random decision-making rule, it's still fine from the fairness point of view. So even though, for example, two arms substantially differentiate in their qualities, a decision maker is allowed to use a random decision-making rule, completely random, so uniformly at random. And needless to say, fair UCB, their version of fair UCB algorithm actually exploit these possibilities. And one of the reasons why it needs to exploit these possibilities is that it's faced with uncertainties. That's why we need the second bullet, and the first bullet we need to achieve no regret property. Now, what we want to do here is basically say that our focus is going to be put on fairness, and we are willing to trade this no regret property for achieving smoothness and maybe a stricter version of meritocratic fairness. Okay, so how do we do this? Well, already in a prior literature, it was noted that for single shot scenarios, certain definitions are achieving this fair smoothness in a sense that, for example, Dwork et al. Knows that fair rules are those that treat similar individuals similarly. So we want to use this definition of Dwork et al. And adapt it to our fairness framework. Basically, we are stealing from other groups. So how do we do this? Well, we need to define basically similarity metrics. And a sensible way to do this in a fairness learning framework would be to say the following. So if we have two arms, blue and red, they can mostly differentiate by reward distributions, as shown on the slide on the left figure, right? So what we want to say is the following: that the probability selection, the difference between probability selection of these two arms is bounded by this gray area, basically bounded by the difference between these probability distributions. Formally, we would have the following definition. So we would say that we achieve smooth fairness for parameters epsilon1, epsilon2, and delta if, with probability that depends on delta, divergence between selection probabilities of two different arms is upper bounded by divergence between reward distributions of the corresponding arms that is modulated by epsilon1 and possibly shifted by epsilon2. Okay? Now, we don't only want to achieve smoothness, we also want to achieve this stricter notion of meritocracy. So how do we do this? So instead of focusing on mean statistic of reward distributions, we sort of analyze the full reward distributions. And the reason for doing so is because in certain cases, you can end up having one arm having higher mean reward value than the other arm, but at the same time, most of the time, this arm actually results in reward realizations that are worse than the other arm. Okay? So we impose the following calibration condition, which states that selection probability of an arm should be equal to the probability that its reward realizations are actually the best among all arms. If you impose this calibration in its perfection, what we gain for free is smoothness with a certain parameters. So if we set this epsilon1 parameter to 2, and if we analyze divergence functions that are equal to total variation distance, then we obtain that perfectly calibrated selections rule also satisfy notion of smoothness. Okay, so basically this calibration rule is our gold standard. However, it cannot be always achieved because of uncertainties. So we don't know these reward distributions a priori. They are not given to us. Okay, so instead of always achieving calibration condition, what we can do is try to aim for it and put it as a soft constraint rather than a hard one. And hard constraint will only be a smoothness condition. Okay? So to this end, we basically define a notion of fairness regret, which measures how much we discriminate an arm when we deviate from calibration condition. And this is exactly what this max operator does for us. So the expression under the summation basically says that when we do discrimination, so when we select an arm with a lower probability than it would be selected under calibration rule, we should put this difference in the regret and sum over all possible arms and all possible time periods. And what to achieve is basically low fairness regret over the full period of multi-arm bandit learning. Now, the definition of calibrated fairness and this fairness regret is not out of the blue. It turns out that there are some connections to a class of scoring functions that are called proper scoring rules. And this implicitly means that we kind of incorporate risk averseness of utility optimizers by defining calibration condition in such a way. We haven't fully investigated this connection, so we leave it for a future work. Okay, now that we know what the fairness constraints are, we also want to analyze different scenarios under different algorithms. So we have basically three fairness scenarios. I will focus mostly on the objective fairness scenario here. The other two are basically either relaxation of objective fairness or refinement of objective fairness. That is to say, for subjective fairness, we relax the goal of acting fairly according to the true reward distribution, in a sense that now we only aim for acting fairly according to the current beliefs about these reward distributions. And in case of dueling bandits, we have a different type of feedback in multi-arm bandit framework. So no longer we have, no longer we see the reward from an arms, but we only see sort of rankings ranking in terms of rewards from different arms. And furthermore, we focus on Thompson sampling as our basic algorithm. This is not surprising because Thompson sampling is actually much smoother than UCB style of algorithms. Okay, so how do we achieve fairness in this objective fairness case? So for this, we basically adopt the structure of deterministic exploration, which is already known in the prior work. And the basic idea would be to try to estimate the underlying parameters of reward distributions. And when we are not certain about them, we just uniformly at random sample arms. Otherwise, we do exploitation phase and use a sub-procedure that we call stochastic dominance Thompson sampling. And in this stochastic dominance Thompson sampling, we basically have two-stage Thompson sampling algorithm. In the first stage, we sample parameter thetas from a posterior probability of thetas given prior reward realizations. And in the second phase, we sample rewards from posterior of rewards given these sampled parameters theta. And finally, we decide to choose an arm which has the highest, the greatest sampled reward. Okay, so this is a bit technical, but intuitively it's really easy to explain. What we basically do is as follows. Suppose that we have two arms, red and blue, and that on a probability simplex, we define basically two zones, red zone and blue zone. Red zone corresponds to the probability that red arm realization of the reward for red arm is greater than the realization of the reward for blue arm, and blue region denotes the same thing but for blue arm. So basically, if P is equal to the probability that realization of red arm is greater than the realization of reward for blue arm, then ideally we would want to select red arm with probability P. However, we don't know this value, so we need to estimate it. And we try to do it from prior rewards. When our estimation pi prime is not good enough, so when the confidence interval in this estimation is too high, we just use uniform and random selection of arms, which basically give us smoothness in our decision making procedure for this case. However, we really want to aim for calibration, which means that when our confidence regarding this P prime value is high enough, we should basically just adopt calibration with respect to P prime. And given the lemma that I explained before, this implies that we are also going to have smooth decision making in approximation. Why in approximation? Well, P prime is approximate version of P, basically. Okay, so we always achieve smoothness, but calibration might not hold for each round. However, we can show that for an appropriate selection of parameters of the algorithm, we actually achieve bounded fairness regret, and this bound is sublinear in the order of total time rounds, right? So on average, we basically go to 0 with this fairness regret. Further on, we can improve on smoothness if we deviate from calibration condition. So intuitively, what you can do is instead of randomizing with P, you can sort of shift this P value towards uniform and random selection, and the whole decision-making rule will be smooth. Okay, so just to conclude, we adopted two notions of fairness. To Bandit setting, smooth fairness and calibrated fairness. We show that calibrated fairness cannot be satisfied for every possible round. So we defined another notion, which we call fairness regret. And then we analyzed Thompson sampling-like algorithms for different scenarios. And we show that they basically have bounded regret. And this bound is sublinear in the order of T, in the order of total number of rounds. For our future work, we would like to include context in our framework, which has already been done for the prior work. Furthermore, we would like to explore this connection between calibration and proper scoring rules, that is risk-averse decision-making. And in case of dueling bandits, we would like to develop our theory for more general ranking models, because at the moment we only have this theory done for Pluckett-Luce models. And I will basically finish my presentation with the final slide, which shows a short overview of different conditions that are relevant for this work. The most related ones are weak meritocracy and smoothness, but there are also some other conditions such as statistical parity and balance and calibration that were designed for single shot scenarios. They are not quite related to our work, but it's interesting to see the comparison. And maybe you can get inspired by this slide when you ask questions. Thank you very much.